Hi, hello there. Welcome to Ethernet switching. If you are planning to become a network administrator or network architect, you will definitely need to know about Ethernet and Ethernet switching. So the two most prominent LAN technologies in use today are Ethernet and wireless LAN or WLAN. Ethernet supports bandwidth of up to 100 Gbps, which explains its popularity. So by the time you have finished this module, you too could create a switched network that uses an Ethernet. Alright, so for the module objectives, the module title is Ethernet switching. And the objective is that at the end of this video lecture, you should be able to explain how Ethernet works in a switched network. So other topic includes Ethernet frame, the Ethernet MAC address, the MAC address table, and switch speeds and forwarding methods. So let's start. Okay, so let's start with the Ethernet encapsulation. So this module starts with a discussion of Ethernet technology, including an explanation of MAC sublayer and the Ethernet frame fields. So Ethernet is one of the two LAN technologies used today, with the other being the wireless LANs or the WLANs. So Ethernet uses a wired communications, including twisted pair, fiber optic links, and coaxial cables. So Ethernet operates in the data link layer and physical layer. It is a family of networking technologies defined in the IEEE 802.2 and 802.3 standards. So Ethernet supports data bandwidths of the following. So you've got 10 Mbps, or also known as the Ethernet, 100 Mbps or fast Ethernet. You also have 1000 Mbps or the Giga Ethernet. You have 10,000 Mbps or 10G, 40,000 Mbps or 40G, and 100 Mbps or 100,000 Mbps, also known as 100G or 100 Gbps. So as shown here in the figure, Ethernet standards define both the layer 2 protocols and the layer 1 technologies. So Ethernet is defined by the data link layer and the physical layer protocols. Okay, so how about data link layer sublayers? Okay, so the IEEE 802 LAN-MAN protocols, including Ethernet, use the following two separate sublayers of the data link layer to operate. So these are the LLC sublayer and the MAC sublayer. Okay, so they are logical link control or LLC and media access control or MAC. So recall that LLC and MAC have the following roles in the data link layer. Okay, so the LLC sublayer or logical link control, this IEEE 802.2 sublayer communicates between the networking software at the upper layer and the device hardware at the lower layers. So it places information in the frame that identifies which network layer protocols is being used for that frame. This information allows multiple layer 3 protocols such as IPv4 and IPv6 to use the same network interface and media. Now the MAC sublayer, this sublayer IEEE 802.3, 802.11, and 802.15, for example, is implemented in hardware and is responsible for data encapsulation and media access control. So it provides data link layer addressing and is integrated with various physical layer technologies. Now let's talk about the MAC sublayer. Okay, so the MAC sublayer is responsible for data encapsulation and accessing the media. So when you say data encapsulation, IEEE 802.3 data encapsulation includes the following. You've got the Ethernet frame, okay, the Ethernet addressing, and the Ethernet error detection. Now, for the Ethernet frame, okay, So this is the internal structure of the Ethernet frame. For the Ethernet addressing, the Ethernet frame includes both a source and destination MAC address to deliver Ethernet frame from Ethernet NIC to Ethernet NIC on the same LAN. Okay, so the last one is the Ethernet error detection. The Ethernet frame includes a frame check sequence, or FCS, trailer used for error detection. So the next is the media access, or the MAC sublayer media access. So accessing the media, as shown in the figure here, the IEEE 802.3 sublayer includes the specifications for different Ethernet communication standards over various types of media, including copper and fiber optic cable. So recall that legacy Ethernet using a bus topology or hubs is a shared half duplex medium. So Ethernet over a half duplex medium uses a contention-based access method. Carrier sends multiple access with collision detection, or CSMA-CD. This ensures that only one device is transmitting at the same time. So CSMA-CD allows multiple devices to share the same half duplex medium, detecting a collision when more than one device attempts to transmit simultaneously. It also provides a back-off algorithms for retransmissions. So Ethernet LANs of today uses switches that operate in half and full duplex. So full duplex communications with Ethernet switches do not require access control through CSMA-CD. Alright, so the next one is the Ethernet frame fields. So the minimum Ethernet frame size is 64 bytes and the maximum is 1518 bytes. So this includes all bytes from the destination MAC address field through the frame check sequence, or FCS field. The preamble field is not included when describing the size of the frame. Okay, so here's the preamble and the SFD. Okay, so with a size of 8 bytes. Okay, so any frame less than 64 bytes in length is considered a collision fragment or runt frame and is automatically discarded by receiving stations. So frames more than 1,500 bytes are considered jumbo or baby giant frames. Okay, so if the frame is transmitted less than the minimum or greater than the maximum, the receiving device drops the frame. Dropped frames are likely to be a result of collision or other unwanted signals, so they are considered invalid. Jumbo frames are usually supported by most fast Ethernet and Giga Ethernet switches and NICs. So the figure here shows each field of the Ethernet frame. Okay, so refer to the table for more information about the functions of each field on the next slide. Okay, now for now, these are the field, preamble, and the start frame delimiter, or SFD. So the preamble, 7 bytes, and the start frame delimiter, or SFD, also called as the start of frame, which is 1 byte in size, making it 8 bytes. Okay, so these fields are used for synchronization between the sending and receiving devices. So these first 8 bytes of the frame are used to get the attention of the receiving nodes. So essentially, the first few bytes tell the receivers to get ready to receive a new frame. So the next one is destination MAC address. Okay, so this 6-byte field is the identifier for the intended recipient. So as you will recall, this address is used by layer 2 to assist devices in determining if a frame is addressed to them. So the address in the frame is compared to the MAC address in the device. So if there is a match, the device accepts the frame. It can be unicast, multicast, or broadcast address. Okay, so the next one is the source MAC address. So this 6-byte field identifies the originating NIC or interface of the frame. So the next one is the type or length. This 2-byte field identifies the upper layer protocols encapsulated in that Ethernet frame. So common values are in hexadecimal 0x800 for IPv4 or 0x86DD for IPv6 and 0x806 for ARP. The next one is the data field. So this field, 46 to 1500 bytes, okay, contains the encapsulated data from a higher layer, which is a generic layer 3 PDU, okay, or more commonly an IPv4 packet. So all frames must be at least 64 bytes long. If a small packet is encapsulated, additional bits called a pad are used to increase the size of the frame to this minimum size. And the last one is the FCS or the frame check sequence. So the FCS field is 4 bytes. Okay, so this is used to detect errors in a frame. It uses a cyclic redundancy check or CRC. So the sending device includes the results of a CRC in the FCS field of the frame. So the receiving device receives the frame and generates a CRC to look for errors. So if the calculations match, no error occurred. So calculations that do not match are in an indication that the data has changed. Therefore, the frame is dropped. Okay? So a change in the data could be a result of a disruption of electrical signals that represents the bits. Okay? Now, let's talk about the Ethernet MAC address. So, MAC address and hexadecimal. So, in networking, IPv4 addresses are represented using the decimal base 10 numbers, okay, and the binary base 2 number systems. So IPv6 addresses and Ethernet addresses are represented using the hexadecimal base 16 number system. So to understand hexadecimal, you must first be very familiar with binary and decimal. Okay, so the hexadecimal numbering system uses the numbers 0 to 9 and A to F. So an Ethernet MAC address consists of a 48-bit binary value. Hexadecimal is used to identify an Ethernet address because a single hexadecimal digit represents 4 binary bits. Okay, so therefore, a 48-bit Ethernet MAC address can be expressed using only 12 hexadecimal values. Okay? So in an Ethernet LAN, every network device is connected to the same shared media. So the MAC address is used to identify the physical source and destination devices, NICs, on the local area network segment. So MAC addressing provides a method for the device identification at the data link layer of the OSI model. So an Ethernet MAC address is a 48-bit address expressed using 12 hexadecimal digits as shown here in the figure. Okay, so because a byte equals to 8 bits, we can also say that a MAC address is a 6 bytes in length. Alright, so you've got 1 byte, another byte, so this one is 3 bytes for the OUI or the organizationally unique identifier, and another 3 bytes for the vendor assigned, making it all in all 8 bytes. Alright, so for example, assume that the company needs to assign a unique MAC address to a new device. So the IEEE has assigned the company a OUI or organizationally unique identifier of, for instance, 0060-2F. Alright, so the company would then configure the device with a unique vendor code such as 3A07BC. Okay, so therefore, the Ethernet MAC address of the device would be the combination, so 00-60 2F, 3A, 07, BC. Right? So that's how we combine it. Okay? So it is the responsibility of the vendor to ensure that none of each devices be assigned the same MAC address. However, it is possible for duplicate MAC address to exist because of mistakes during manufacturing. So mistakes made in some virtual machines implementation methods or modifications made using several software tools. So in any case, it will be necessary to modify the MAC address with a new NIC or make modifications via software. All right. So how about frame processing? So sometimes the MAC address is referred to as burned-in address or BIA because the address is hard-coded into a read-only memory or ROM on the NIC. So this means that the address is encoded into the ROM chip permanently. All right. So note that on modem PC operating systems and NICs, it is possible to change the MAC address in a software. So this is useful when attempting to gain access to the network that filters based on the BIA or the burned-in addresses. So consequently, filtering or controlling traffic based on the MAC address is no longer secure. Okay? When the computer boots up, the NIC copies its MAC address from ROM into RAM. When a device is forwarding a message to an Ethernet network, the Ethernet header includes this. Okay? So you've got the source MAC address and the destination MAC address. So basically, the source MAC address is the MAC address of the source device NIC. And the destination MAC address is the MAC address of the destination device NIC. Okay? So you've got what you call an automated figure. Okay? Now in here, if you will observe, right? So you've got the source address and the destination address. And of course, the data with it. Okay? So note that the Ethernet NICs will also accept frames if the destination MAC address is a broadcast or multicast group of which the host is a member. So any device that is the source or destination of an Ethernet frame will have a device NIC and therefore a MAC address. Okay, so this includes workstations, servers, printers, and routers. Okay, so try to see the animations on this presentation. Okay, so basically every data moved by the computer towards the other or towards the destination should contain a source and destination MAC address. So it will be broadcasted over the network, but only the computer who owns the destination address will open the frame. All right. Okay, so how about the Unicast MAC address? So in Ethernet, different MAC addresses are used for layer 2 unicast, broadcast, and multicast communications. So a unicast MAC address is the unique address that is used when the frame is sent from a single transmitting device to a single destination device. Okay, so if you will observe here the animation on the right, okay, so see the figure. Host 1 is sending data to this workstation having the MAC address of 0007 E942AC28. So this is an example of a unicast addressing. So in the example animation, okay, a host with IPv4 address 192.168.1.5, this is the source, requests a web page from the server at IPv4 unicast address 192.168.1.200. So for a unicast packet to be sent and received, a destination IP address must be in the IP packet header. So a corresponding destination MAC address must be present in the Ethernet frame header. So the IP address and the MAC address combine to deliver data to a specific destination host. Okay, So the process that the source host to determine the destination MAC address associated with an IPv4 address is known as the Address Resolution Protocol, or ARP. Okay, so the process that a source host uses to determine the destination MAC address associated with an IPv6 address is known as ND, or neighbor discovery. Okay, so take note that the source MAC address must always be a unicast. Okay, so the next one is broadcast MAC address. So an Ethernet broadcast frame is received and processed by every device on the Ethernet LAN. So the features of an Ethernet broadcast are as follows. Okay, so it has a destination MAC address of FF, 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 FF in hexadecimal, or 48 ones in binary. Okay, next, it is flooded, or it is platted out all the Ethernet switch ports except incoming port. So if you will observe on this animation here, okay, so it is forwarded on all the ports of the switch. Okay, so that is a broadcast. Next, it is not forwarded by a router. So if there is a router here, so router is a non-broadcast device. So it will not be forwarded on the other side of the router. So if the encapsulation data is an IPv4 broadcast packet, this means that the packet contains a destination IPv4 address that has all ones in the host portion. So this numbering in the address means that all hosts on the local network broadcast domain will receive and process the packet. All right, so the next one is a multicast MAC address. Okay, so an Ethernet multicast frame is received and processed by a group of devices on the Ethernet. So this belongs to the LAN to the same multicast group. So the feature of an Ethernet multicast frames are as follows. Okay, so there is a destination MAC address, for instance, of 01, okay, 005E. When the encapsulated data is an IPv4 multicast packet and destination MAC address of 33, okay, that's 33, okay, when the encapsulated data is an IPv6 multicast packet. So there are other reserved multicast destination MAC address for when the encapsulated data is not an IP, okay, such as Spanning Tree Protocol, or STP, and Link Layer Discovery Protocol, or LLDP. Okay, so it is flooded out all the Ethernet switch ports except the incoming port, unless the switch is configured for multicast snooping. So it is not forwarded by a router unless the router is configured to route multicast packets. Okay, so if the encapsulation data is an IP multicast packet, the devices that belongs to a multicast group are assigned a multicast group IP address. So the range of IPv4 multicast address is 224.0.0.0, okay, to 239.255.255.255. Now the range of IPv6 multicast address begins with FF00::/8. So because multicast addresses represents a group of addresses, sometimes called a host group, they can only be used as destination of a packet. So the source will always be unicast address. Okay? So as with the unicast and broadcast addresses, the multicast IP address requires a corresponding multicast MAC address to deliver frames on the local network. So the multicast MAC address is associated with and uses addressing information from both IPv4 or IPv6 unicast address. Okay, now if you will observe from the animation here, okay, So take note that host 1, okay, I need to send a group of hosts or to the group of hosts on the network. Okay, so this pertains here to the first 3 computers as a destination. Okay, so this is what you call multicast address. All right, wherein the frames is forwarded to a group of computers over the network. Okay, so next section would be the MAC address table. Okay, so let's talk about the switch fundamentals now. So now that you know all about the Ethernet MAC addresses, it is time to talk about how the switch uses these addresses to forward or discard frames to other devices on the network. So if a switch just forwarded every frame it received out all ports, your network would be so congested that it would probably come to a complete halt. Okay? So a layer 2 Ethernet switch uses layer 2 MAC addresses to make forwarding decisions. It is completely unaware of the data or protocol being carried out in the data portion of the frame, such as an IPv4 packet, an ARP message, or an IPv6 ND packet. So the switch makes its forwarding decisions based solely on the layer 2 Ethernet MAC addresses. So an Ethernet switch examines each MAC address table to make a forwarding decision for each frame, unlike legacy Ethernet hub that repeat each out all ports except the incoming port. So in the figure here, all right, so the 4-port switch was just powered on. Okay, so the table shows the MAC address table, which has not yet learned the MAC addresses for the 4 attached PCs. Okay, so note that addresses are shortened throughout this topic for demonstration purposes. So we just use here MAC 00.0A instead of having a complete MAC address. Okay, so the MAC address table is sometimes referred to as a content addressable memory or a CAM table. So while the term CAM table is fairly common, so for the purposes of this course, we will refer to it as MAC address table. Okay, so next is examining the source MAC address. So we call it learn. Okay, so the switch dynamically builds the MAC address table by examining the source MAC address of the frames received on a port. So the switch forwards frames by searching for a match between the destination MAC address in the frame and an entry in the MAC address table. So in examining the source MAC address or learn, every frame that enters a switch is checked for new information to learn. So it does this by examining the source MAC address of the frame and the port number where the frame entered the switch. So if the source address or if the source MAC address does not exist, it is added to the table along with the incoming port number. So if the source MAC address does exist, the switch updates and refresh timer for that entry. So by default, most Ethernet switches keep an entry in the table for 5 minutes. So in the figure here, for example, PCA, okay, is sending an Ethernet frame to PCD. So the table shows the switch adds the MAC address for PCA to the MAC address table. Okay, so it is in here. So port 1, that is the MAC address of PCA added on the MAC address table. So note that if the source MAC address does exist in the table but on a different port, the switch treats this as a new entry. So the entry is replaced using the same MAC address but more concurrent or more current port number. Okay, so again in the diagram here, PCA sends a frame, okay, to the switch, and the switch adds that port number and MAC address for PCA to the MAC address table as shown here. All right, so the continuation. So find the destination MAC address or forward. So if the destination MAC address is a unicast address, the switch will look for a match between the destination MAC address of the frame and an entry in its MAC address table. So if the destination MAC address is in the table, it will forward the frame out of the specified port. So if the destination MAC address is not in the table, the switch will forward the frame out all ports except the incoming port. So this is called an unknown unicast. So as shown in the figure, the switch does not have the destination MAC address in its table for PCD. So it sends the frame out all ports except port 1. Okay? So if you will observe here, we only have one MAC address listed on the MAC address table, and that is for PCA. Okay? So the destination MAC address is not yet listed here. So what will happen is the switch will forward the frames to all the ports except on the incoming or where the frame originated. We call it the incoming port. Okay? So note, if the destination MAC address is a broadcast or multicast, the frame is also flooded out all ports except the incoming port. Alright? Okay, so next is filtering frames. So as a switch receives frame from different devices, it is able to populate its MAC address by examining the sources or the source MAC addresses or source MAC address of every frame. So when the MAC address table on the switch contains the destination MAC address, it is able to filter the frame and forward out a single port. Okay, now in that case, since we have already the entry on the MAC address table, so therefore the data or the frame from host A will be forwarded directly to the destination, which is the MAC address of host D here. Okay? So next would be PCD to switch. So we are not yet done. Okay? So in the figure, PCD is replying to PCA. So therefore, PCD will be having it forwarded first on the switch. Okay? So the switch sees the MAC address of PCD in the incoming frame on port 4. So the switch then puts the MAC address of PCD into the MAC address table associated with port 4. Okay? So the switch adds the port number and the MAC address for PCD on the MAC address table. Okay? Next, because the switch has destination MAC address for PCA in the MAC address table, it will send the frame only out port 1 as shown here. Okay? So it is directed towards host A having the MAC address of 000A as indicated on the MAC address table. Okay? So next would be the PCA to switch to PCD. Alright? So next is PCA sends another frame to PCD. So the MAC address table already contains the MAC address for PCA. Therefore, the 5-minute refresh timer for that entry is reset. So next, because the switch table contains the destination MAC address for PCD, it sends the frame only out of port 4. So the switch receives another frame from PCA and refreshes the timer for the MAC address. Okay, that would be an entry for port 1. So the switch has a recent entry for the destination MAC address and filters the frame, forwarding it only on port 4. Okay, so that's how Ethernet operates, okay, using a switch. Okay, so moving the data from the source to destination and the reply from the destination going back to the source. All right, so let's go ahead on the next subtopic, which is the switch speeds and forwarding methods. So frame forwarding methods on switches, specifically on Cisco switches. Okay, so as you learned in the previous topic, switches use their MAC address tables to determine which port to use to forward frames. So with Cisco switches, there are actually two frames forwarding methods, and there are good reasons to use one instead of the other. So depending on the situation. Okay, so switches use one of the following forwarding methods for switching data between the network ports. So these are the store and forward switching and the cut-through switching. So for the store and forward, this frame forwarding method receives the entire frame and computes the CRC, or the cyclic redundancy check. So the CRC uses a mathematical formula based on the number of bits or ones in the frame, so to determine whether the received frame has an error. So if the CRC is valid, the switch looks up to the destination address, so which determines the outgoing interface. Then the frame is forwarded out of the correct port. Okay, so the next one is cut-through switching. So this frame forwarding method forwards the frame before it is entirely received. So at a minimum, the destination address of the frame must be read before the frame can be forwarded. So a big advantage of the store and forward switching is that it determines if a frame has errors before propagating the frame. So when an error is detected in a frame, the switch discards the frame. Discarding frames with errors reduces the amount of bandwidth consumed by corrupt data. So store and forward switching is required for the quality of service, or QoS, analysis on a converged network where frame classification for traffic prioritization is necessary. So for example, voice over IP or VoIP data streams need to have priority over web browsing traffic. Okay? Now, in a cut-through switching, the switch acts upon a data as soon as it arrived or it is received. So even if the transmission is not complete, the switch buffers just enough of the frame to read the destination MAC address so that it can determine to which port it should be forwarded out the data. So the destination table, or the destination MAC address, is located in the first 6 bytes of the frame following the preamble, as presented earlier. Okay, so the switch looks up the destination MAC address in the switching table, determines the outgoing interface port, and forwards the frame onto its destination through the designated switch port. So the switch does not perform any error checking on the frame. Okay? Next, so there are two variants of the cut-through switching. You have the fast-forward switching and the fragment-free switching. So what's the distinction between these two? So for the fast-forward switching offers the lowest level of latency. Okay, so fast-forward switching immediately forwards a packet after reading the destination address. Because fast-forward switching starts forwarding before the entire packet has been received, there may be times when the packets are relayed with errors. So this occurs infrequently, and the destination NIC discards the faulty packet upon receipt. So in fast-forward method, latency is measured from the first bit received to the first bit transmitted. So fast-forward switching is a typical cut-through method of switching. So the second one is the fragment-free switching. So in a fragment-free switching, the switch stores the first 64 bytes of the frame before forwarding. So fragment-free switching can be viewed as a compromise between store and forward switching and fast-forward switching. So the reason fragment-free switching stores only the first 64 bytes of the frame is that most network errors and collision occurs during the first 64 bytes. So fragment-free switching tries to enhance the fast-forward switching by performing a small error check on the first 64 bytes of the frame to ensure that the collision has not occurred before forwarding the frame. So fragment-free switching is a compromise between the high latency and high integrity of store and forward switching, and low latency and reduced integrity of a fast forward switching. Okay, so some switches are configured to perform cut-through switching on a per port basis until a user-defined error threshold is reached, and then they automatically change to store and forward. So when the error rate falls below the threshold, the port automatically changes back to cut-through switching. Okay? Now, memory buffering on switches. Okay? So an Ethernet switch may use buffering technique to store frames before forwarding them. So buffering may also be used when the destination port is busy because of congestion. So the switch stores the frame until it can be transmitted. Okay, so as shown here in the table, there are two methods for memory buffering. So you've got the port-based memory and you've got the shared memory buffering. Okay, so shared memory buffering also results in a larger frames that can be transmitted with fewer dropped frames. This is important with asymmetric switching, which allows for different data rates on a different port. So therefore, more bandwidth can be dedicated to certain ports. Okay, so example, this is a server ports. Okay, having, for instance, 10 Gbps or 1 Gbps ports. Okay, so the next one is duplex and speed settings. So two of the most basic setting on a switch are the bandwidth, sometimes referred to as the speed, and duplex settings for each individual switch port. So it is critical that the duplex and bandwidth settings match between the switch port and the connected devices, such as computer or another switch. So there are two types of duplex settings used for communications on an Ethernet network. So it could be full duplex, both ends of the connection can send and receive simultaneously, or half duplex, only one end of the connection can send at a time. So auto negotiation is an optional function found on most Ethernet switches and NICs. So it enables two devices to automatically negotiate the best speed and duplex capabilities. So full duplex is chosen if both devices have the capability along with the highest common bandwidth. Okay, so in the figure here, the Ethernet NIC for PCA, okay, can operate in full duplex or half duplex in 10 Mbps or 100 Mbps. So PCA is connected to switch, okay, switch 1 on port 1, which can operate in full duplex or half duplex and in 10 Mbps, 100 Mbps, or 1000 Mbps. So if both devices are using auto negotiation, the operating mode will be full duplex and 100 Mbps. Okay, so you've got full here, and they agreed to set the negotiation or the speed up to 100 Mbps. Right? So duplex mismatch is one of the most common causes of performance issues on 10-100 Mbps Ethernet links. So it occurs when one port of the link operates at half duplex while the other port operates at full duplex, as shown here in the diagram. Right? So switch 1 is operating in full duplex and switch 2 is operating in half duplex. So this would lead into duplex mismatch. Okay, so duplex mismatch occurs when both or one port on a link are reset, and the auto negotiation process does not result in both link partners having the same configuration. So it can also occur when the user reconfigure one side of the link and forget to reconfigure the other. So both sides of the link should have auto negotiation on, or both sides should have it off. So best practice to configure both Ethernet switch ports as full duplex. Okay. Next is the Auto-MDIX. Okay. So connections between devices once required the use of either a crossover or straight-through cable. So the type of cable required dependent on the type of interconnecting devices. So for example, one device identifies the correct cable type required to interconnect switch to switch, for instance, or switch to routers, or switch to host, or router to host devices. Okay, so with that, we are using a specific type of switch. Okay, so a crossover cable is used when interconnecting devices like router to router or PC to PC. Okay, and straight through cable is used for connecting unlike devices, router to switch, okay, switch to host. Okay, so we can use a straight through cable. Okay, so take note that a direct connection between a router and the host requires a crossover cable. Now with the MDIX turned on, so this will automatically detect and automatically adjust. Okay, so depending on the type of cable used. All right, so that's a good thing about the Auto-MDIX. All right, so most switch devices now supports the automatic medium dependent interface crossover or Auto-MDIX feature. So when enabled, the switch automatically detects the type of cable attached to the port and configures the interfaces accordingly. So therefore, you can use either a crossover or a straight-through cable for connections to copper 10, 100, or 1000 port on the switch. So regardless of the type of device on the other end of the connection. So thanks to Auto-MDIX feature. Okay, so the Auto-MDIX feature is enabled by default on switches running the iOS release 12.2 or later. So however, the feature could be disabled. For this reason, you should always use the correct cable type and not rely on the Auto-MDIX feature. So the Auto-MDIX can be re-enabled using the MDIX Auto interface configuration command.